So in this video we're going to do the first of two examples where we calculate the volume between two surfaces. So in this example it says set up the double integral to determine the volume of the solid region bounded by the graphs of z equals x squared plus y squared and x squared plus y squared equals 4 and z equals 0, which is just the xy plane. So if you kind of draw a picture of what's going on here, z equals x squared plus y squared is a paraboloid. It's an even function, so it's going to have xz, yz plane symmetry and symmetry with respect to the z-axis. So we're going to be, and x squared plus y squared equals 4 is going to be a cylinder of radius 2 that also has symmetry with respect to the z-axis. So we're going to be able to use symmetry to calculate this volume. So that's the first thing that we want to recognize. And z equals 0 is just the xy plane, so we want the volume above the xy plane. So because I know I'm going to be able to use symmetry to do this calculation, I'm going to do 4 times a double integral. I'm going to calculate the volume in octant 1 and multiply it by 4. So if I just draw an octant 1 picture of what's going on here, my paraboloid is going to look something like this in octant 1. And then there's a cylinder of radius 2 extruding from the xy plane, so it's going to be coming up and intersecting the paraboloid at some point. And what I want to recognize is that I want the volume between the plane and the surface. The surface above is actually going to be the paraboloid. And if you were having a hard time visualizing things, again, what you want to do is graph it in GeoGebra until you get good at drawing and visualizing. So here's my cylinder, x squared plus y squared equals 4. Here's the paraboloid, x squared plus y squared. And it's going to be the volume between the xy plane right here and the surface above. So to set up the bounds of integration on this, it's because in this case we're just wanting to set the double integral up. So in the xy plane I either need to run parallel to the x or the y axis. If I run parallel to the y axis, I would be running from the line y equals 0, which is the x axis, up to the circle. But the circle is just x squared plus y squared equals 4. So y would equal, and I just need the positive square root because I'm working in octant 1, so 4 minus x squared. So run up to the boundary of the circle, square root of 4 minus x squared. And then this is a circle of radius 2, so in the x direction we would be running from 0 to 2. The surface above is the paraboloid, so it's x squared plus y squared. The surface above, and then I integrated with respect to y first and then with respect to x. So there's a setup for that integral, taking advantage of symmetry. If I didn't take advantage of symmetry, if I didn't take advantage of symmetry, here's how it would look different. So I'd have my dy dx. When I did this, I'd get plus or minus the square root, so we'd have to be sweeping behind, and we'd have to be dealing with the whole circle. So we would be running from negative square root of 4 minus x squared in the y direction all the way to the positive square root of 4 minus x squared. And then we would have to run from negative 2 to 2 along the x-axis. We'd have to... So symmetry, like I said, symmetry really can make our life easier. You can see the bounds of integration here are much less satisfying. It's always really nice to get zeros on those lower bounds of integration. They are incredibly useful for simplifying calculations.